Thank you, Karen, and thank you for having me today. Hi, everyone. So my name is Jerry. I am from Splunk, and today I'm going to talk about how Splunk is using Pulsar IO. The agenda for today's presentation, first I'll give a quick overview of Pulsar IO. I think there are already a couple of presentations at the summit that already went over it, so I will be quick as possible to provide an overview. Then I will talk about how, in general, Pulsar is being used at Splunk. And then I will talk about how Pulsar IO is being used at Splunk. Further, I'll talk about the improvements that we made to Pulsar IO and the underlying Pulsar Functions framework at Splunk and the contributions we've made back to community. Lastly, I will talk about kind of what our roadmap and for Pulsar IO is at Splunk. Let me first provide a quick overview of Pulsar IO. So what is Pulsar IO? At its core, Pulsar IO is a connector framework to ingress and egress data to and from Pulsar. So when we talk about in the Pulsar IO platform, a source is just basically a connector, a resource that ingresses data into Pulsar, a Pulsar topic, or could be a list of Pulsar topics from an external system. And a sink is a resource that basically egress data from typically a Pulsar topic, or a list of Pulsar topics to an external system. So why does Pulsar IO exist? And let me talk about some of the rationale for having a connector framework for Pulsar. So Pulsar IO was designed really to find the answer to several of these questions. One is, what is the best way to be moving data into and out of Pulsar? And the next question is, well, where should I run that application that basically publishes or consumes data from Pulsar, and how I should run my applications to publish data and consume from Pulsar. So those are all questions a developer developing a custom application to read and write from Pulsar will typically need to answer. And Pulsar IO is really there to basically answer, provide a platform and a system to answer those questions for them. So let me go over some of the design goals for Pulsar IO. The number one is that it has to be easy to use. For regular users, I'm talking about non-developers, just users of Pulsar, they should be able to easily ingress and egress data without having to actually write any code. And that's kind of the main goal that we want Pulsar IO to be is, look, we will have experts, or developers of Pulsar write, a good set of connectors, and then users could just simply, submit some of these connectors to run and instantaneously be able to bring, data in or out of Pulsar. The other thing we really that's part of the ease of use story is a feature called built-in connectors, so that users, especially if you're running Pulsar in the cloud or as a service for your organization, that the user does not necessarily need to submit any sort of package that contains all the code for the connectors, that the user simply needs to submit, okay, I want to run this connector, and it will run. So we have the idea of built-in connectors that does exactly that, is that, when the admin or the developers of Pulsar deploy the cluster, they can bundle basically connectors, prepackaged connectors with the Pulsar function workers and deploy them in a way that in a configuration of a built-in connector, so that users do not actually have to submit any packages to run them. The next thing is managed runtime. It's one of the key features that answers a lot of the questions I posed earlier. Is one of the goals is obviously to not worry a user about how or where to run a connector. Things like execution scheduling, scaling, and fault tolerance should be taken care of by the runtime, and the user should just really worry about configuration and maybe business logic, and running an actual executing the connector should be managed by the cluster and the runtime. Also, this is one of the goals is to have a flexible runtime. This is really a tool targeted towards Pulsar cluster admins. Like they're the ones that really kind of determine, well, how do I want to run these connectors? Should I run them as threads, processes, or even Kubernetes pods / containers? There's different trade-offs in terms of isolation and costs among the three different kind of ways you can run them. So we would and different, I think, use cases probably have different requirements of isolation or different requirements of costs. So we want to be able to provide a flexible runtime, a flexible solution to people that's actually operating the Pulsar cluster. Just to briefly kind of show kind of the Pulsar IO API for both the source and the sink. It's relatively simple. A source has an open method that opens potentially connections to an external platform and initializes basically those clients. And then you have a method where you can just read and return data that you've read. And eventually you can also, if you have some custom logic you want to implement for close, you can also, when a connector is shut down, you can appropriately close connections and so on and so forth. And that's kind of the basic life cycle of a connector there. And it's similar to kind of what a sink is. You also have an open method. You have a write method, which basically will get called. That these are basically when the underlying kind of Pulsar consumer reads a message from a topic, it will basically be returned to this write method, and then you can write that record to the desired external system. And the sink also has a close interface to clean up anything when the sink is needed to be terminated. So let me also talk about kind of the architecture and execution of Pulsar IO. Like Pulsar IO, like I mentioned previously, is really built on top of the Pulsar Functions framework. And because of that, it inherits all of the features and benefits of the Pulsar Functions framework. And in this kind of diagram, in this slide, the deployment configuration here is known as kind of is deployed in kind of a cluster mode, in which you will be able to submit in a cluster mode where the worker and the function worker and the broker is co-located in the same process or container, so that basically users could submit function requests or function CRUD requests to any of the brokers to also start functions, sources, and sinks as well. So let me go over some of the benefits of Pulsar IO. These are also really benefits of Pulsar Functions, but I think it's worthwhile because Pulsar IO and Pulsar Functions, basically share the, core set of benefits and features. One of them, like I said before, is, deployment flexibility. You can run a custom sink or source by submitting kind of the code on the fly, or you can kind of use the built-in model, whichever one you feel is the appropriate for the use case you want to do. And execution flexibility. Sources and sinks can run as part of a kind of an existing cluster, like I kind of showed before, kind of run as an existing cluster. Or if you don't really want to have a cluster kind of manage that lifecycle for you, you can always feel free to run that as a standalone process on Kubernetes. At Splunk, we also have certain use cases in which we do that. Like we basically deploy source or sink or even function instances as standalone Kubernetes pods, and then use kind of a HPA to auto scale them as well. So that's also a strategy you can employ if you want to be more kind of lightweight about your deployment, or you want to control your deployment in a more fine-grained manner. So another thing for especially running in kind of the cluster mode is parallelism. It allows you to kind of increase the number of instances for sources and sinks dynamically when they're still running. It's simple. It's as easy as basically making a making a configuration change. There's an API to say, okay, I want to, instead of running one instance of this source, I can run now 10 instances of source, basically as a way to increase performance and increase throughput for that sink or source. Load balancing, especially also a feature in cluster mode, is that when you submit your connector, your signature source, the number of instances is kind of evenly distributed across all the workers, so that it's not just all of the instances are running at a particular worker or a particular node. So there's the load balancing is also taken care of for you. Also in cluster mode is the fault tolerance, monitoring, and metrics. Like if you're submitting your connector to kind of a cluster, the cluster will basically monitor the source and sinks, and if nodes fail, the instances will get redeployed, and metrics are automatically collected for the sources for instances as well. Another thing, like I mentioned, for dynamic updates, it's really simple to make configuration changes, whether that's parallelism, whether that's a connector specific config change. You can make them on the fly, and make them on the fly while the connector is still running. Pulsar IO, because it also is built on Pulsar Functions, also leverages the state API offered by the Pulsar Functions. So Pulsar IO, if needed, can also have access to persistent state. So this is useful, for example, if you're reading a large file from say S3 and you want to periodically checkpoint your progress in case of failure, state could be used for something like that. That was a brief overview of Pulsar IO. There's a lot more details. I would encourage everyone to go in, kind of play around, and do a deeper dive into Pulsar IO. And I've listed some resources here. So now getting into kind of the more interesting things is how Pulsar and Pulsar IO is being used at Splunk. This is kind of touched up a bit, and Karthik's keynote yesterday of how Pulsar is being used at Splunk, but I will go talk about it a little bit more here as well. So Pulsar at Splunk is used for both streaming and queuing use cases. Streaming as in kind of stream processing use cases where data has to be processed in order, while queuing use cases is more kind of data can be processed out of order in kind of a work queue fashion. So at Splunk, we use Pulsar for both types of use cases. We have deployed Pulsar as a multi-tenant SaaS offering internally for other teams and other organizations within Splunk to kind of leverage the capabilities. And one of the things we really want to kind of position Pulsar at in Splunk is Pulsar. We're positioning Pulsar as the data nervous system at Splunk, where where Pulsar is the de facto platform to basically move and route data between different systems and also connect apps and services together. So this is one of the use cases, and one of the key use cases of Pulsar at Splunk is to power kind of the data ingest and data routing and the DSP product offering. So Pulsar. So this diagram here presents kind of the high-level architecture of how Pulsar is used in the DSP Splunk product, both on-prem and in the cloud. As you can see, Pulsar is used as a way for many different types of data, and many different modes of data ingestion, and all lands in Pulsar, which then can be read by a stream processing engine. We at Splunk, we use Splunk to process that data and potentially write out to another another Pulsar topic, or some sort of external system. So at Splunk in DSP, there's really at Splunk there's only kind of three categories of data ingestion. One is through kind of the HTTP HEC protocol. It's a proprietary protocol developed at Splunk for ingesting data into Splunk via kind of HTTP. The other one is called S2S, which usually is the format that is forwarded to by forwarders, Splunk forwarders, if people are familiar, that are run on machines that can be forwarding machine logs and so on and so forth. They get ingested into Splunk, and then the next one is the kind of the more interesting and the more relevant to Pulsar IO is connectors. A lot of different types of connectors, reading from S3, CloudWatch metrics, GCS. Those are connectors that users could deploy to basically ingest data from and into Pulsar, and then further do some data processing on that data. So Pulsar IO, how is it being kind of used at Splunk? So as I kind of touched up on in the previous slide, Pulsar IO is used to power the connector framework of the data stream processor platform, we call kind of this internal framework the unified connector framework. Why we kind of chose, just didn't call it Pulsar IO is we did add some, abstractions on top of Pulsar IO. There is a control plane and there is some, automatic configurations that we do for certain connectors. So, but at the core, we are basically just using Pulsar IO to power this whole connector framework, and it's really responsible for kind of data ingress and data egress for the DSP platform. So let me kind of go into why Pulsar IO was chosen as Splunk, were the decisions and involved, and why we really wanted to use Pulsar. So there were existing existing connector frameworks at Splunk, especially in the DSP product, to ingest data. But there were the platform that was developed was is homegrown. It was proprietary, and it suffered kind of from several design decisions that one of them had complex architecture, which meant to have scalability issues, which then you would infer had performance and infra cost implications. And one of the more important thing is maintainability, because if it's homegrown, proprietary, like once people come and go, it's hard to hire more people that are really kind of to know the platform and to have a understanding of what's really going on. So there's definitely an eagerness to kind of leverage what is already in open source, right? And since we're already using Pulsar, Pulsar is already kind of being positioned as kind of a message, a data hub, a data nervous system. So why not leverage the open source and the existing kind of frameworks in open source that are built to basically ingress and egress data into Pulsar. So there was a lot of due diligence we did in terms of comparing Pulsar IO to the internal kind of proprietary connector frameworks, and at the end of the day, like, it was a clear decision for us to say, okay, let's retire the legacy platform and leverage open source. So let me kind of go over a little bit more in detail how, especially in DSP, how kind of Pulsar IO is being leveraged. This is kind of a more detailed architecture diagram than the one I presented before about DSP. So everything that in DSP, the data stream processor at Splunk, is run on Kubernetes, and really the key piece of the that's relevant to kind of the Pulsar IO is the unified connector framework, which basically we also deploy a cluster in Kubernetes, and it's not exposed directly to users or internal users, but it's really hidden behind kind of an API server control plane that we implemented to add some additional functionality and control over what connectors can be deployed and lifecycle management. But at the core, where basically all the connectors are powered by Pulsar IO and that framework to basically ingest data from a variety of sources into Pulsar. So let me go over kind of the use cases for Pulsar IO at Splunk. One of the use cases is obviously getting streaming data into Pulsar, the generic kind of reading from maybe another streaming source, reading from another kind of in a streaming fashion where data is unbounded and the source kind of continually pulls for new data to be ingested into Pulsar. But there's also another kind of use case that has arisen at Splunk, is kind of this idea of large scale data collection. Is how do we collect kind of a more or less a large amount of static data and ingest them into DSP. And an example of that would be look like if a user or a customer of Splunk had log data into S3 or GCS, and they want to bring it into Splunk or DSP for processing, how can we ingest that data efficiently into DSP and Splunk? So some of the requirements we've laid out here is, it needs to be able to ingest, petabytes of data per day, run tens of thousands of connector instances, have low startup time, and be kind of cost effective. And I'll talk about a little bit further later in my presentation how we, have improved Pulsar IO and Pulsar Functions framework to kind of achieve, all of these things. So one of the things we've also innovated on for and contributed to open source is the idea of kind of the Pulsar IO batch source. As I said in my earlier slide, one of the key use cases is the idea of large scale data collection of especially static data to move it into kind of Pulsar. So this is really designed for large amounts of static data, like for example AWS or GCS. The batch source instead is a little different than the vanilla kind of Pulsar IO source, which I mentioned earlier, kind of continually reads from an unbounded source. But the batch source has kind of a map reduce like behavior, which there's a kind of a discovery phase, and then there's a collect phase. In the discovery phase, in this phase we basically go and discover kind of what data needs to be collected, and then we split, and then we determine we create a list of tasks or splits or partitions, as you will, to basically, or just kind of a list of work to be done, so to be done to fully collect that data. So the discovery phase is usually can be triggered by user-defined logic, but a lot of times it's kind of triggered periodically. For example, if I want to go to some file server FTP to download some files, I want to go kind of do like maybe every once every hour or once every half an hour, depending on the use case. So it's triggered kind of in a periodic sense, and the discovery is only run kind of on one instance 0, and this is done kind of for a very good and specific reason. Like currently, all of this can technically be implemented by just the vanilla kind of Pulsar source. If you want to, if you can still, but the problem with that is like typically each instance of the source will have to do a discover themselves and then figure out which what is, and then partition the data using some sort of deterministic hashing function to determine, okay, this is the set of data I am responsible for. So especially it creates a scalability issue. Is if you have a lot of instances, you have to go and kind of fetch and discover that data. And this is problematic, especially for kind of cloud providers, AWS, where they kind of really heavily rate limit you on how many metadata requests you can do. But in reality, if you really think about it, it's unnecessary for every single instance to kind of go and see what, the amount of work needs to be done, the way that needs to be done, kind of at one place. One instance need to figure out what is all the work, and then just split it into tasks or splits, and then basically send them out for other kind of workers to do. And that's kind of the idea here behind the discovery phase and the batch source. And the next kind of the actual phase of collection is called the collect phase, where all the other instances as part of this connector will read from kind of a queue that the discoverer or the discovery phase will output is a list of tasks that will read. The collect phase, all the other workers will, and including kind of instance, will read from this kind of a task queue and then execute those tasks by executing those tasks, which usually is pulling data, for example, a file or a part of a file from for example S3 into Pulsar. And obviously all of the instances are run in parallel, and they're crunching these tasks in parallel. And as you would imagine, kind of ordering is not so much required in kind of these scenarios where we can just basically in parallel ingest files or ingest files into Pulsar. So this is kind of a diagram to illustrate how some of the stuff works. As I mentioned earlier, there's a trigger that periodically triggers kind of the discovery, which then outputs a list of tasks into this task queue, and the underlying underlying system that is used is just a Pulsar topic, and then other instances read from this task to get work, and then execute those tasks to fetch data from remote sources, and then eventually write it to the configured output, output topic. And to go over kind of the batch source API, it's fairly similar to kind of the actual source API. There's an open method, but the additional methods that kind of are added is discover method, which basically is the logic to discover the list of tasks that the discover phase needs to output. So that consumer there, that called task eater, is basically you're supposed to return or consume a list of tasks that the other kind of that needs to be done for this kind of cycle of the source run. And the other kind of interesting thing is the trigger. As I mentioned before, typically triggering is usually done on some sort of cron schedule periodically, but if you have some sort of custom use case, you can implement some custom triggering logic to trigger when these batch source collections should happen. And let me talk about how we're deploying kind of Pulsar IO as Splunk. So we are deploying function workers separately of brokers. Function connector instances are run as threads within the worker process versus the other methods such as running, as individual processes or even as containers. The reason why we kind of chose this kind of this mode, even though you can say it has the lowest level kind of isolation because they're just run as threads within workers, is because look, the connectors we are running is vetted code. It goes through kind of code reviews, and these are connectors developed internally by Splunk developers. So we trust the code is not arbitrary code someone is running and deploying. So that's kind of one of the reasons why we decided, look, running as threads is perhaps the best option here. And obviously, given the scale that we're trying to basically run the connectors or Pulsar IO at, running as threads is really lightweight and definitely saves on infra costs and resource consumption compared to kind of the other modes such as running as process or containers. So we are currently deploying, leveraging the feature built-in connectors. So when we kind of deploy, update worker, when we start connectors, they're really kind of we're not submitting any packages dynamically. The packages for the workers are already located on the worker containers. So that it really kind of one of the benefits there is it allows us to control what we run, very very carefully, so that the versions across the different connectors, we know for sure what versions of connectors are running because they're essentially baked into all of the worker images as well. And it also greatly speeds up startup time because we're not submitting a package and then downloading it on the worker and so on and so forth. And we're also using state store as we're also deploying a state store cluster that's kind of deployed as a separate cluster as well to offer a kind of table service for connectors that require stateful behavior, stateful use cases as well. So one of the things I really want to touch up on, for my team and working on Pulsar at Splunk is we're really deeply supportive of open source, and we contribute a lot and work a lot with open source. So just kind of a brief list of the things that we at Splunk have contributed to open source. Obviously it's the batch IO source that I mentioned previously, but also in order for us to run at the scale we kind of really want, we've really redesigned core pieces of the Pulsar Functions architecture to improve scalability and stability, and I'll touch up on that in some subsequent slides. We've also done a large number of performance testing, and this is kind of how we've noticed what we need to do to improve scalability and stability. So we've done performance testing for running 100,000 instances, 10,000 sources, 10 instances each with petabytes of per day ingest rates to kind of test the core stability and the core performance of the underlying platform. We've also made tons of, I didn't list individual ones, but we've listed tons of bug fixes as well as performance fixes for the platform as well. So I want to go into detail about since we're kind of running out of time here, I won't go into much detail about the specific improvements. One of them is in regards to metadata compaction. Before we made this improvement, the metadata topic, which is an internal topic used by Pulsar, was not could not be compacted. So as time goes on, that topic grows indefinitely, and we have reworked some of the internals to allow that to happen. And this is still kind of an ongoing process. We definitely have made quite a few improvements, but there's still some work to be done to push it all the way to completion. The other thing is scheduling and performance and stability. There was a lot of kind of bottlenecks in terms of scheduling and stability issues, and we've gone in and we reworked how kind of the master worker schedules assignments, and that now has is working a lot better and able to kind of scale to a lot more number of instances. And we have added the idea kind of we have also integrated kind of the use of the exclusive producer, which Matteo talked about in another slide, another talk. One of the motivations for creating the exclusive producer was for Pulsar Functions, is because we have the idea of a worker, like a leader in the worker worker cluster, and it's responsible for actually writing the metadata and assignment topics. We have a single kind of writer model, and we need the kind of the guarantee of an exclusive producer to make sure that only one guy, the actual leader, is writing to these topics. So there's not any sort of two leaders writing to these topics to corrupt kind of the underlying data. So we really have leveraged the exclusive producer, and we added that capability to allow Pulsar Functions and underlying framework to really kind of work correctly with high levels of guarantee. Well, we've also added improvements and kind of rebalancing and scheduling aspects. I won't go too deeply into that, but there's automatic rebalancing mechanism that we added so that the load across workers can be more more well distributed. I'll touch up on kind of what we're thinking about the future of Pulsar IO at Splunk. We're planning on adding a lot more interesting and useful auto scaling features, especially with workers and instances. We already started kind of work on the auto scaling workers on Kubernetes using HBAs, and that work is almost done. In the future, we might also think about resource aware scheduling in situations where if we see kind of a high level of heterogeneous kind of workloads and the cluster. We'll continue our work to get topic compaction to work fully with the internal topics and Pulsar Functions, and really push that through. Another interesting area we're looking into is integrating kind of the client memory limits to Pulsar Functions, because we're kind of running instances of sources and sinks as threads. We kind of we understand there's not a lot of isolation protection there, but what can we do to get a little bit more of it? And we're going to add per producer and consumer memory limits so that there is a bound on how many network buffers a particular instance can use, and use that as a way to kind of throttle and really kind of limit the amount of resources a particular connector instance can use. And obviously, we're going to continue to make fixes and optimizations as we go along. And then I kind of want to talk to you about some of the future-looking things that we're trying to do with Pulsar IO at Splunk. We really want to kind of create this idea of connectors as a service based on Pulsar IO. It's a kind of a platform to run all connectors, at Splunk, and it's going to be kind of powered by Pulsar IO, because we're positioning kind of Pulsar as the data nervous system, as the data hub. It really kind of makes sense for us to provide a service for the broader organization to say, okay, I want to ingest data from this location, And the kind of the underlying abstraction is, okay, that data will then land in a topic, and then you can use the the data in the topic, fetch the data from topic and feed it into other systems. And if you kind of want to egress your data, you can also kind of write it as an abstraction into another topic, and then use a connector to egress that data to an external system. So we are really kind of looking into and developing this idea of connectors as a service at Pulsar IO to power kind of all connectors running at Splunk. And this is the idea, like I mentioned before, is connectors as a service really is the bridge between external platforms and Pulsar, which is going to be kind of the data hub. And then from there, the data can be routed and be go to the many other services and destinations within Splunk as well. And this is kind of a more specific kind of diagram of what we're thinking about connectors as a service. As you can see, like connector as a service is in between external platforms and kind of messaging as a service, which is Pulsar, and it can pull data into topics as well as write data out from topics into external sources. And then once it gets to Pulsar, it can also be routed to individual things like Flink, indexers, and other services that can basically use the data that landed in a particular topic from either an external platform or say the output of another internal service within Splunk. So definitely very excited about kind of that effort to really fully leverage the potential of Pulsar IO at Splunk. So that kind of concludes my talk. Thank you for listening, and we are definitely hiring at Splunk. We have a great team of many Pulsar experts and PMC and committers, both in Pulsar proper project as well as in Bookkeeper as well and Zookeeper. So yeah, we're a great team. So if you're interested in working on hard systems and distributed systems projects, especially at scale, please let me know. We are hiring.